Welcome back, everyone. The journey so far has been incredible. Well, the Three.js team just issued a new, official challenge on X, highlighting a beautiful animation, and I thought, we have to build this. After watching it closely, I realized there's a deep secret to how it works. This is episode 4. Let's solve the challenge.
To start, create a new folder for our project, and inside it, a file named index.html. First, we declare our document type. Next, our HTML tag. Inside that, the head. We'll give it a title, Radial Wave Challenge Anim theme. And we'll link our style sheet, which we'll create next. Now for the body. Inside, we need our import map to load Three.js. Inside the script, we define our imports for 3 and 3/add-ons. Finally, we load our own script with a script type module src script.js. Our HTML is ready. Next, create a new file and name it style.css. This will be very simple. We'll use a universal selector asterisk to set margin 0 and padding 0. For the HTML and body, we'll set overflow hidden and a dark background. Background color equals 111. And for our canvas, we'll set display block. The styling is complete.
Now for the main event, create your script.js file. First, we import our libraries. Import *s3 from 3 and import orbit controls from 3/add-ons/controls/orbitcontrols.js. Let's create our scene. Next, our camera. I'll use a perspective camera and position it with camera.position.set 10, 15, 10 for a nice angled view. Now, the renderer. We'll create a WebGL renderer with anti-alias set to true. We set its size and pixel ratio. And this time, to get those beautiful shadows, we need to enable them. Type renderer.shadowmap.enabled equals true. Then, we add the renderer's canvas to our HTML document. Let's add our orbit controls for navigation. Now for the lighting, which is crucial for this scene. First, an ambient light. Think of this as the base level of light in the room. It softens all the shadows. I'll set it to white with a low intensity. Next, our main light source, a directional light. This will act like our sun, casting the distinct shadows. We'll set its color to white and its position up and to the side. We must tell it to cast shadow equals true. And for better quality, we'll increase its shadow map size.
It's time to build our grid of cylinders. First, we define the shape. Const cylinder geometry equals new 3.cylinder geometry of 0.15, 0.15, 116. This is a cylinder with a radius of 0.15. For the material, we'll use a mesh standard material, which reacts nicely to our lights. Now, let's define our grid. Const grid size equals 35, and const spacing equals 0.5. This will give us a 35 by 35 grid of cylinders. The total number of cylinders will be grid size times grid size. For performance, we'll use InstancedMesh. We create it with our geometry, material, and the total count. And we must tell it to both cast and receive shadows. Then we add it to the scene. Now, we need to prepare some data for our animation. This is the secret to the effect. We'll create an array to store the minimum distance for each cylinder. Const min distances equals new float32 array, total cylinders, and an array to store the 2D position of each cylinder. Const cylinder positions equals square brackets. We also need our dummy object 3D to help us position each instance. Now let's create the grid. We'll use a nested loop. The outer loop runs for I from 0 to grid size. The inner loop runs for j from 0 to grid size. Inside, we calculate the x and z position for each cylinder. Const x equals I minus grid size divided by 2 times spacing. We do the same for z. This centers our grid at the origin. We push this new x and z position into our cylinder positions array. Then we set the dummy object's position, update its matrix, and set the matrix for the current instance. Close both loops. Our grid of static cylinders is now built. But what will they react to? We need to define the shape that will create the wave. We'll create an array called shape points. For this example, we'll use a simple circle as our shape. We'll define a shape radius of 5. We loop 100 times, and for each step, we calculate a point on a circle using math.cosine of angle for x and math.sine for y. We push this 2D point into our shape points array. Now, for the most important pre-calculation step, we need to find, for every cylinder in our grid, its closest point on that shape path we just created. We'll loop through every cylinder for let I equals 0 to I less than total cylinders I++. Inside this loop, we'll set a min distance to infinity. We get the current cylinder's position, then we start another nested loop, this time through every point in our shape points array, for let j equals 0 to j less than shape points.length j++. Inside this loop, we calculate the distance from the cylinder to the current shape point, and we check if distance is smaller than min distance. If it's smaller, we found a new closest point, so we update min distance equals distance. Close the inner loop. After checking all the shape points, the min distance value holds the distance to the absolute closest point on that shape path. We store this value in our min distances array. Close the outer loop. All the hard work is now done. We have a list that tells every cylinder its exact distance from our hidden shape.
Let's build our animate function. Inside, we'll call requestAnimationFrame and get our elapsed time from a new 3-clock. Now for the core animation logic. We'll loop through every single cylinder from I equals 0 to total cylinders. Inside the loop, the first thing we do is get the pre-calculated min distance for the current cylinder from our min distances array. And now for the wave math, which is surprisingly simple now that our data is prepared. Let's define our wave parameters: wave frequency, wave speed, wave amplitude, and a fall-off value. The fall-off will make the waves get smaller as they move outwards. Here is the magic formula. Const wave equals sine of min distance times wave frequency minus elapsed time times wave speed. This creates a sine wave based on the cylinder's distance from the shape, and it moves over time. Now we calculate the final height. Const scale y equals 1 plus wave times wave amplitude times math.exp times min distance times falloff. We're using math.exp here with our falloff value to create a really smooth and natural decay of the wave. We also calculate the position y to be half of the scale to keep the cylinders grounded. Now we just apply these new values. We get the current matrix for our instance, we get its current position, we set the dummy's position with the new position y and its scale with the new scale y. We update the dummy's matrix, and we apply that new matrix back to the instance. Close the loop. And the most important line for instanced mesh animations, instancedCylinders.instanceMatrix.needsUpdate equals true. Finally, we update our controls and render the scene. At the end of the file, we add our resize handler and call animate to start everything. Let's save and see the result.
And there you have it. Challenge accepted and challenge solved. We've used InstancedMesh for performance, Trigonometry for placement, and a beautiful radial sine wave for the animation. This is a perfect example of how the fundamental building blocks we've been learning can be combined to create truly stunning professional level effects. Thanks for taking on the challenge with me. Happy creating.